Dr. Restuccia finished his studies at the University of Ferrara. Then his doctoral thesis was made in the Escuela Superiore Sant'Anna de Pisa, and then he translated to Valencia to finish his master's thesis. Where in this master, he began to develop a resource allocator for heterogeneous NOC architecture. That is network chip architecture. From this moment, he has improved these aspects, and currently he owns several implementations about thread modeling, about AXI interchip communication, AXI interchip communication. And in this conference, he is going to talk about the last study that he has implemented, collaborating with AMD and other enterprises from their factories. And I hope that you enjoy and learn a lot from.
Thank you, Fernando. Thank you, Fernando. Thank you. So yeah, today I'm going to talk more about on-chip communication. Like, it's a work that we've done with many companies, Intel, AMD, and other companies. I have a list of collaborators afterwards, and this is like my hardcore research stuff. But at the lab we have a lot of other stuff going on, and I have a summary about that. So first of all, a disclaimer to start with. That is the one that I just made. So this is just like my hardcore research, but I work at KRG Lab, Customer Research Group Lab, and we work a lot on embedded systems, FPGAs, security verification, low latency hardware acceleration, and AI engines with Pablo that he was visiting us, and many other projects. So if you're interested in any of these, please, we can talk later, and eventually I can put you in touch with the relevant people. Also, I will keep some part of this talk pretty high level, so I will not dig into too many details for time reason. But if you have questions, please stop me. I'm happy to make this interactive. So yes, yeah, sure.
You need to take your microphone.
Yes. Para él. ¿Está bien? Well. I'm getting pretty confused in going between Spanish, English, and Italian. So I don't know what language I'm going to speak tomorrow. But yeah, anyway. So yeah, I'm happy to make this an interactive conversation. So if you have questions, stop me. There are a lot of concepts and a lot of papers. So Fernando already introduced me, but just like to have a background, what I did, what I'm doing. Right now, I'm a staff R&D engineer at UC San Diego, working with Professor Kastner. I was postdoc researcher with him before, and before that, I did my PhD in Scuola Superiore Sant'Anna in Pisa with Professor Giorgio Buttazzo. So it's a safety and security lab, basically. My research focus are on hardware security, functional safety, and real-time system, and we did a lot of work on that too. Safe acceleration at the edge, we have a couple of works on that, and open source system on chip platforms, mainly collaborating with the people that developed this platform, such as E.T.S, Zurich, University of Bologna, and Columbia University. So my journey lies at the intersection of security and safety for complex applications, and our aim is to use open source as a driver for democratizing access to more safe and secure system on chips. So the roadmap of the contribution is going to be here. First of all, we're going to start with talking about some hardware security. And the main contribution that we did is formalizing system-level security and safety threats. Plus, we developed transparent and high-performance RTL-level defensive solutions to be integrated in the system on chip. And this is a set of the contribution that are all connected among each other. Second of all, about the safety and real-time systems. And what we did is developing timing predictable frameworks for upper bounding the execution time on heterogeneous system on chips for critical applications. In particular, we've been focusing on the on-chip communication part, so the interaction in shared resources, interference, and isolation, basically. And third, the open source system on chip platforms. So the things that we did and we proposed, we wanted to make them useful for the community. So we applied them directly to these platforms, and they are integrated with these platforms. And I'm going to show you one system on chip that we did in collaboration with E.T.S Zurich and University of Bologna that integrates these technologies. An integration of our access control system into a network on chip based platform made by Columbia University. And an analysis, the first analysis, real-time analysis at the hardware level of a full system on chip for predictable computing. So some marketing here. So where this topic relevant? I'm not going to go through the things that we have. We need computing and more and more computation, AI, and everything. Pablo yesterday already talked about that. So I mean, we already know the story, right? What is interesting from our perspective is that the SoCs are becoming more and more application specific. So you make your SoC for your application, basically. And this raises complexity in design, verification, and security and safety. The third-party API integration is particularly interesting for us. So whenever you develop a system on chip, I have some slides on that. You buy IPs from external sources. You buy your CPU, you buy an accelerator, you buy your memory, and what happens when you put them together? It's an interesting thing, basically. So there is a big open hardware momentum, which is very interesting for us, given by RISC-V, but also all of the labs like E.T.S Zurich, University of Bologna, and E.T.S and Columbia University that are doing a fantastic job in that, and they publish that online. So these are focused mostly on performance. And what we wanted to do is like giving some touch of safety and security to this for accessing more secure and safe platforms. All right, we start with a background first, right? So if it's something that you already know, please stop this like, hey, Francesco, let's go ahead to the real gig. So if we look inside the system on chip, I think that some people here, how many people have been working with FPGAs here? I mean, Pablo, I know, yeah, of course. So this is a Zinc UltraScale Plus. The system grammar of a Zinc UltraScale Plus, and basically the point here, this is the careful SoC that I'm going to show you before. But the point is, if we look from the perspective of this talk inside of the system on chip, we want to make a taxonomy of what is inside here. The taxonomy is that it is composed of multiple modules, and we can classify them as controllers, the one on the top, peripherals, the one at the bottom, an interconnect in the middle. In this case, it's an AXA interconnect. And this is just another representation of the same, but implemented on an FPGA, basically. We did a lot of experimentation on FPGA. So again, with our controllers, processors, DMAs, hardware accelerators, everything, right? So these are the master, historically named master, now called managers of the system bus. So these ones are the ones that initiate the transaction. They say, I want to speak with something. I want to go to the memory, right? I want to go to the I/O. So they send requests. The peripherals at the bottom are the memories, the I/Os, etc., that are the ones that respond to these requests. And historically, they've been called slave or subordinate on the system bus, that they just serve transactions. They don't initiate transactions. And then in the middle, there is a system interconnect that is made of crossbar, FIFOs, adapters, bridges, that makes the communication happen. So I didn't say one thing. They're made of hardware modules. These modules, as I mentioned before, they're coming normally from external sources. You might develop something internally. But these, as they come from external sources, they're generally called IPs, hardware IPs. So intellectual property models that you buy and integrate when you do your system on chip, when you make your system on chip. So where do these IPs come from? Like the hardware models that you use to build the system on chip? Well, it's not practically to internally develop all of them. Think about developing a CPU, right? So they come from different sources, internal teams, external vendors, open source projects, eventually partners, whatever it is, okay? So you buy these chips, so like I buy this CPU, I buy this GPU, I buy the X accelerator, whatever it is, I buy this memory controller, and then I want to put them together. So what is the industrial methodology? So this is a very nice picture from E.T.S. I'm not part of E.T.S, so I wrote over there that there are other systems from Cadence, ARM, and Synopsys, but it's a nice picture that demonstrate how it works, basically. So you take your IPs, you put them in some sort of this framework that generate an interconnect for you and generate all of the system integration files, and it generate the verification eventually. And you got basically your file for verification, and then of course you go down through all the GDS2 for doing the actual chip. Okay, but these chips we say are heterogeneous, so they come from different sources, so they need to speak a common language, right? Otherwise, how they can communicate between each other? The answer to this question is an on-chip communication standard, and in this case, I'm focusing on ARM AMBA AXI. So AXI stands for Advanced Extensible Interface, and is the de facto standard for on-chip communication, both in open source systems and in open source IPs, and also in the industry. So why this is the standard? Well, it has very nice features. So the first and more interesting for industry is that it's royalty-free. So you can use it basically for free. But it's also very flexible, and it's a very mature standard, and it defines it has a very lightweight definition for what we can say lightweight data sheet of 300 pages, but yeah. In any case, it defines a manager to subordinate interface, mostly. Then there are some other things that are defined, but mostly the interface. And so defining just the interface, you can put in the middle whatever you want. So you can put an hierarchy of multiple crossbars, you can put a network on chip, you can put rings, you can put whatever you want. And besides that, it's very high performant and flexible. So it allows multiple outstanding transactions, burst transaction, auto further completion, and it supports for advanced features from ARM like MTE, PAC, pointer authentication, and PAM, and all of these other features. Concluding the background, the threat model. So what do we care about here in this with this work? So we have a simplified SoC over there. The interconnect can be whatever. In general, what we focus on are the managers. So just because the managers are the one that initiate the transactions, are the one that can make the more damage. Or even the interconnect can make damage, for sure. The peripherals can make damage, for sure. But the aim of our studies were on managers, mostly. So we treat interconnect and peripherals mostly as trusted. So, and we want to say, what happens when we integrate IPs, managers IPs, CPUs, other accelerators, and you might have them that are malicious. They might be faulty. They might be greedy. They might be misbehaving, right? Or they might be used with intent of implementing a software attack. So you basically misconfigure the IP and use that for a DMA attack. This is a very common scenario too, right? So what can happen is that attackers can leverage the bugs in the on-chip communication for making nasty thing happenings. But the most interesting part for our studies was leveraging the lack of specifications of the standards. So the standard is flexible, there are lacks of specification, and if you go into that, you can stay compliant with the standard by having some very nasty behavior that can break the security and the safety of the system. And what we demonstrated and observed, bandwidth stealing, denial of service in the access of shared resources, and also data leak in some implementation. All right, we start with the first set of contributions. So far, so good. Questions? Are good? Okay. Was the background enough, Fernando? Was the background enough?
Yes.
All right, perfect. All right. So this was the first work where everything, we begin with everything, right? So we were working with FPGAs at that time. And it was like 4 or 5 years ago now, so it's some time right now. But we were saying, okay, we have hardware accelerators and FPGA and critical systems. We want to integrate them. How can we be sure that we can upper bound the communication between the accelerator and the memory controller and the memory to upper bound the execution of a critical application, right? And there we opened the Pandora box. And this is the first thing that we found, basically. So anyone that has been working with these platforms, the FPGA system on chips, knows that if you do something like if you blink too fast, like from an hardware accelerator perspective, everything breaks, right? So, and this first issue that we found is summarizing is that controllers have capability of issues heterogeneous transactions, so multiple lengths of transaction, and this is allowed by the standard, basically. When you take multiple of them, you put them together, and you might not be able to verify what they are going to do runtime. So they can actually influence each other access to the bandwidth, which means that they can steal bandwidth through each other, basically. So and the root cause here is that AXI features 5 channels. They are independent. There is no control among the multiple channels. And also, generally speaking, a round-robin vanilla arbiter is implemented in the interconnect that does not take into consideration how long the transactions are. So basically, you might expect that you have an AXI interconnect that is round-robin, and you have a fair access to, like for multiple, you have 3 hardware accelerators. You say like, okay, I have 33% access to the bandwidth. No, you have like 2% or something like this, right? So, and we made experiments on that, right? So we changed the transactions, like the transaction size of multiple hardware accelerators, and we saw that from, in this case, the R3, from 33% access to bandwidth, you can get, 3%, something like this. I don't remember the actual number, but yeah. So this is clearly a problem from a safety perspective, and at that time we were focusing a lot on safety, but it's also a security problem for availability perspective. So what we did here is say like, okay, what can we do to solve this problem? We want to be transparent. We don't want to change the interconnect. We don't want that the hardware accelerator are constraints. So what can we do? Basically, we said, I have a next slide on that. We said like, okay, let's put ourselves in the middle here. And we put some lightweight model, and we control them, we configure them, and we equalize the transactions. So basically, if there are transactions that are too long, we split them. And if there are transactions, when they come back, we merge them together such that the solution is completely transparent to the hardware accelerator, right? So, and this is easy to integrate, as I mentioned, and the impact on that is that it was the first work that we started with, but also is the one that provides fair bandwidth allocation in the car-field SoC. So how it works, I already gave you a look before. From this architecture, when you just have interconnect and accelerators, you put something in the middle, we call them ABE, AXI burst equalizers. And basically, you configure them, you control them. You decide, you say like, okay, the burst length maximum that you can access is 16 bits, not more than that. If you send a transaction to 256, we split them transparently. You don't even know about that, right? And so what we've been able to achieve is that these are the response times with and without our system, and these are the bandwidths associated with the response times. So without our system, if you change the configuration of the others, you can go up to 10 times the response times of a fair bandwidth allocation. So which is really a problem, right? But instead, when we put this in the middle, we stay exactly like the same, and we have an impact on performance that is less than 1%. We just have a 1 clock cycle time for doing the actual splitting and the merging eventually. Second issue, denial of service. This is even more interesting, I believe, and it creates even like a more interesting scenario. And what is interesting is that we observed this in commercial IPs from AMD. So the high-level idea here is that the standard itself is made for high performance. And you say, okay, if you are an accelerator and you want to make, or a CPU or whatever, GPU, you want to make write transactions, you can submit a request for writes for up to 256 data words. It's not important the length. But what the standard says is that you can send a transaction. If the transaction is propagated through the interconnect, that transaction is valid for you, and the bus is booked for you. As long as you don't provide the data, the bus is yours. All the bus through the memory, it's yours, meaning that you can keep the bus as long as you want. So what happened, basically, we made experimentation on that. First of all, on FPGA, we developed our RTL to understand what was going on. But then we started an investigation, and we used the DPU accelerator from AMD from the VTSAI framework. And that was like 2021. So I think it was DPU 2.0. I don't remember. I don't know if this is like still the behavior, but I suppose so. And basically, what we saw is that these commercial APs, what they do is that when they have to write something, they send a request of write, but they send it speculatively. So they want to access the bus so greedily, of course, because they want to get data fast and they want to access the memory fast. But being that greedy, you basically stole the bus for all of the others in the system. So you basically apply on the denial of service of access. And in this case, it's limited from the point of view of the DPU. It's just for performance. It's just greediness. But this can break the performance of the others. But if you have a malicious intent or something, you can denial of service as long as you want. All right? So, and the root cause here, again, is the lack of specification in the standard plus some the implementation of the switching policy at the interconnect level. So cut through interconnect strategy, which is the high performance one, of course. And the implicit trust assumed in the standard, which is another thing. So what we did here, our contribution is that at first we did an investigation of the problem, as I mentioned, and then we did a formalization, modeling, and analysis of the issue, basically. At the beginning, we were looking at that from a real-time system perspective. So we did an analysis, and we said, how can we leave flexibility to the accelerators to be greedy, but not that greedy? So like, give me some greediness, but not that much, okay? So, and we did an analysis, like a closed formula analysis that is in the paper. If you're interested, we can discuss about that later in detail. That is based on the slacks of the hardware accelerator. So we find the slack time, the minimum slack time of a task set of hardware accelerator. And the minimum one is like a stall budget that you can greedily access the bus without providing data. If you ask more than that, you're cut out of the system, and we restore the access to the others. So we need to do some restoring cleanup, some house cleaning, because the standard itself does not allow to abort transactions, but we are capable of giving back the access to the memories and the rest of the system for the other accelerators. And the second contribution that we made is that after seeing that as a real-time performance problem, we said, how can we solve this in an easier way? So when you have to do it from a real-time perspective, you need to know the task set, you need to know how many transactions are made, you need to know the periods, you need to know everything. But it's a problem when you do best effort or mixed critical. So we developed a smart buffering, let's say, technology that can be integrated inside of the interconnect. We call it cutting forward, which is something in the middle between cut through and storing forward. And this is configurable, and it basically pipeline the data validation phase with the data propagation phase. And in this way, we can split and validate and propagate the data without propagating the stall downstream in the interconnect. So this had a particular impact, and we did submit a CWE about that. CWE is common weaknesses in enumeration from Mitre, for the people who doesn't know about them. And they have both a software and a hardware list. And this has been pre-approved, and it should be approved soon. It should become a CWE for chip designers. And also this is integrated in the SoC that we're going to see later. So after that, we say, okay, we have two problems. So we have to put two models to solve that. Say like, no, we make our own interconnect. So we make our own interconnect focusing safety and security. And in particular, at that time, we were working with FPGAs. And in particular, we virtualized application on FPGAs, mainly on the PS core, but also using the accelerators part. So we say we need an extension of the hypervisor on the PL part, on the FPGA. So let's make an interconnect that is an extension of the hypervisor. It basically monitors and supervises the access to the memory and the IOs from the hypervisor perspective. And this is the AXA hyperconnect. It's a one-to-one substitute. We wanted to make it transparent. So you just place it in, that's it, done. From the point of view of the accelerators of the system, it works. And what we did, there is an RTL design, it's kind of old, it's not published, but we can talk about that if you're interested in accessing the RTL. Plus, we integrated with an hypervisor from a company in Italy. So yeah, I think we got everything here. Oh, we got some internals here from AXA Hyperconnect. And basically, what it does is like the burst equalization, the delay, and the denial of service prevention. But also, we integrated an access control system that we developed, and is going to be the next topic. Not next, but after this. Yes?
I was curious about
Sure.
this solution that you are presenting. You work on with the version of the data, right?
So I was discussing this with I don't remember who, that any PhD student started working with Vivado. Like, yeah, I was with him, right? So my Vivado version is 2018.2. So that's mine. But these are RTL, so you can integrate them. So they are RTL level, they are WHDL, and basically you can just like make your own model for Vivado 2035 point whatever, and you just integrate them. Yeah.
So the standpoint is like, okay, this version.
I'll take it, Fernando. Sa.
So I was wondering to know if those problems that you find with this particular version of Vivado, of the axis,
Sure.
and so on and so forth, that started for you the point of research. Do you know if these problems
Are still there?
are still there?
I think so.
They updated
No, the thing is standard more. It's more the standard level than the implementation level. So AXI defines the standard, and then you implement on top of the standard. If you want to go for performance, you just look into performance, you're going to have these problems. Because if you want to solve this, you have a cost to pay, right? So either you have like a switching policy that is not cut through, which is the highest performance one, or you have to put something that monitors what's going on, or you have to split transactions basically of the accelerators. So it's more at the level of standard. So here we analyzed the AXA interconnect and the AXA smart connect from Xilinx, and now AMD. But we didn't have access at that time of the ARM interconnect, the NIC 400. But if you look at the datasheet, they implement the same switching policy, and I suppose that there might be something similar too. Yeah.
So the next question, before jumping to another.
Sure.
You mentioned something about a company. So are you selling or
No.
or whatever these IPs, new IPs
No.
through Sala?
No. I'm not selling anything. No. I'm just a pure academic guy.
Company.
No. I am a pure academic guy. No. We just we didn't publish some of this work because this work is from a few years ago now, and at that time we didn't publish that. Like hardware was not like now. Everyone published like hardware, but at that time it was not common. But no, I mean it was just for implementation, and there are like fully working prototype is the key word, right? So they need to be deeply verified, but it works. Yeah.
Francesco, one question. Is this new interconnects compatible? Do they overlap with the functionality of the AXI firewall?
AXI 5, you say? Yeah.
AXI firewall, do you know that?
The firewall, yes, sure.
How is the relation?
So basically they are related in the sense that they do something very similar, but the AXI firewall was later than us. Yes.
Maybe they complement because the AXI firewall is about, okay, if I see that one communication is installed because one AXI
Sure.
slave for mass devices, dies? I'm going to just.
They actually, so again, I don't know the full functionality of the Axi firewall. I know that they have an Axi hanging monitor for subordinate. This is old. The Axi firewall is something that came out maybe a couple of years ago. Something like this, like 1 year ago, 1.5 years. So I think that they provide functionality in the Axi firewall for even access control, maybe they do. So they kind of, they're kind of related, let's say. They provide the same functionality, yeah. But so I like to think that maybe they got inspired by this work. So I like to think, I don't know. But I mean, good. All right. So another project, this is a slightly different project. What we have after? Okay, access control. But it's still related to on-chip communication. But in this case, it's more related to verification. So we saw that IPs can misbehave on the bus freely and create issues. So we said, like, okay, we're not capable of finding them before we integrate them in the system on chip. So basically, the reason is that the VIPs, the verification IPs for Axi, might not capture completely the loopholes of the standard, right? And we've been looking into the Xilinx one at that time. There are commercial ones that we don't have access to, so I don't know, maybe they might. But openly available, there was not a set of properties for the hardware to say, like, what should I check when I put an accelerator inside of a verification framework and try asserting properties, basically. So we did this work, we started this work in collaboration with Shweta Schindler at E.T.S Zurich a couple of years ago. And basically the idea here is that we provided a framework of security properties, basically. So you have a set of properties for Axi, and they are for functional, some for safety, some for security. And these properties can be integrated in your verification flow and used to check, like, if there are some sort of these problems into your IPs before integration. So we made this to be easily expandable. So because I'm sure that there can be other interesting things to look into the protocol. And we're talking with Aru about that right now, actually. And basically, yeah, this project aims to raise the hardware security verification before the integration. So the first one were defense, so like runtime defense. These ones are more verification, so you use them before to check that you're not going to eventually have these problems. All right, I mentioned access control. Question, no? Okay. I mentioned access control before. This is still like a work from 3-4 years ago. And at that time, we were analyzing the new CWEs. And we saw that the CWEs, most of them, are related to access control systems. Like, I don't have the table here, but I think that the 2025 list, there are 11 most important CWEs, and out of 11, 5 are related to access control. And mostly these are related to problems in verification of the access control system, so bugs that goes past the verification phase. So at that time was missing a design and verification framework for access control, for SoCs. So we said, all right, we want to do something. We don't want to be the smartest in the room and say, like, we do an access control that is secure. So what we do is that we provide an RTL, but we also provide a set of properties that maps to CWEs. And these properties, you can use them to verify that the access control system is secure. And even if you don't trust us, deploy your own properties and put them on top of ours or remove ours and verify that, right? So that was the idea of Acre, the Acre project. And I mean, it's a simple access control system. So basically, you have something here that works as an I/O MMU, basically. And after that, the RISC-V I/O MMU has been specified, but not. I don't think they got inspired by that, but it was specified afterwards. And what we did also is like having an open Titan hard root of trust managing at runtime the access control systems and the policy. So that was the idea of the framework. I think I said everything about that. This is also like a wrapper based, like it's a wrapper system. You integrate it in directly, and you can manage it. Like you can access it with an XI communication port, and you basically manage the access control policy. All right, we finished with hardware security. We go into safety. I'm gonna stay higher level with that because I'm losing you already. No, I'm still here. With real time, so the work before, like the defensive methodologies, served also as a baseline to have a known, to know how the managers can access the bus. If we don't know that, we can't make any upper bounding of the system interaction because anything can happen. So you can access, you can delay the bus, you can access the bus, whatever you want. So that baseline helped us make the analysis of the system interaction. So basically what we did is that the motivation is that there were no upper bounds analysis that could be directly applied on the hardware level, so at the IP level, and we wanted something very fine-grained, so the level of granularity of the cycle, of the clock cycle. So we made a modeling of interconnects deployed on FPGAs, hierarchical, so it's not just for flat interconnects, but for multiple hierarchical interconnects. And we modeled the hardware accelerator, we modeled the interconnect, and we modeled the task set that runs on the hardware accelerator. So like the periods, the amount of transactions, and how many multiple transactions you can issue, how long are the transactions, and how the interconnect can digest that. So how long are the queues? So what is the arbitration and everything? And we build a formula, like a mathematical analysis in multiple lemmas and theorems at the end. And basically this is to upper bound at the end the execution time of an hardware accelerator accessing memory. This is the first work, is the base analysis, and we use this as a further. We use this further for upper bounding the execution time of the DPU core that I mentioned before. So we were running CNNs on FPGAs, and we wanted to upper bound that, for instance, for E.T.S application, so autonomous cars. So at that time, there were CNNs. Now CNNs are gone, but we made running multiple CNNs for object detection, some YOLOs, some SSDs, some plate detection, etc. And we did a reverse engineering of the DPU, in particular of the access to the bus, to understand how the DPU execute. And with the execution model of the DPU, we understood the transaction issued, and we upper bounded the execution for each of these DNN model. But also what we did is that we found that there was a big conflict in the access between instructions and data for the DPU. So the FPGA ZC102 UltraScale Plus has two different memories. So there is a DRAM memory and there is a non-chip memory. It's called OCM, I think. Yeah, OCM memory. So the OCM memory is very small, but it can fit most of the models that are running on the DPU, the instructions for the model. So we said, like, okay, let's split that. Let's put the model inside of the OCM, like the instruction of the model, and we keep the data and like the images and everything in the RAM. So we split that, and we developed a model to sneakily split. I mean, these frameworks are not very friendly to be used. So we developed a small model, an RTL model that we placed in the middle of the manager interface that is issuing requests for instructions, and we basically redirect the addresses from DRAM to OCM and get the data from there. So Yeah, and this basically provided the second validation of our methodologies, and we were able to upper bound the execution time of all of these deep neural networks. All right, finally, the work that I'm more proud of, which is, yes?
One quick question, Francesco.
You like DPU, I know.
I know the answer, but on the memory accesses from the DPU code, from your experience, from the point of view, do you think that a full cache hierarchy makes sense? And another kind of
A full cache hierarchy?
Hierarchy, yeah, from the PL, in order to try to cache memory accesses from the DPU, does it make sense?
So from the instruction perspective, maybe. From the data perspective, maybe not. So like if you have two different interface, right? So the data interface is a very like streaming based interface. It's like long burst transactions. It's like getting like images. So it needs to like fetch like large amount of data. So in that case, like having a cache is not very useful. From the instruction perspective, it might be, but you can also like, if you have space, you can also bring your instruction on chip, basically. So you say like, okay, I want to be like the fastest possible. I just place a VRAM here. I put the instruction there. They're not that big. It depends on how big is your model, right? Mm-hmm. So, but yeah, that can make sense. Sure.
Okay.
All right. So I was saying the work that I'm more proud of, which is the conclusion of all of the work that we did, which is Carfield. Actually, this is not a work that I did. I just contributed to that, which is a system on chip made by Luca Benini's team at E.T.S Zurich and University of Bologna. And what is this? Is an application-specific system on chip for critical applications, like automotive, but not only. RISC-V based for AI-enhanced critical application. I think this is the marketing for, of course, yeah, important, right? So it's fully open source. And if you look online, you find the whole RTL and verification and everything for this. So it's very cool to play with. The most important part, from my perspective, the most interesting part, not important, the interesting part is the predictable access interconnect, which is there in the middle. So this access interconnect deploy the methodologies that we were discussing at the beginning for hardware security. So there is a bar splitter, there is a cut and forward, which is the one to stop the stalling of the bus. And there's a bandwidth reservation unit, which is another thing that we've been working with in our lab. And basically, yeah, it is made to provide robust system-level interactions among the multiple controllers. And here we have multiple. There is a safety island with 3 cores, 3 RISC-V cores that execute in lockstep. There is a security island with a full open Titan. And there are memories, and there is a full cluster for hardware acceleration. So, yeah. I think we got that, yeah. Okay. The other contribution is Bastion, which is secure third-party integration on network-on-chip platforms. And this is with Columbia University. So Columbia has a different platforms that is network-on-chip based. It's called ESP. So in ESP is a fantastic platform. Also open source, if you want to work with that, it's a great platform. There are limited features for security, though. So we teamed up with them, say like, okay, we want to do a framework for that. What do you think about that? Sure, let's do it. So the work on access control that we did, we make it more lightweight, and we created a socket for the network on chip. So we created a security socket that is placed between the normal socket and the queue, basically. So before the router or the network on chip. And this socket are managed by a security plane. And in one of the tiles here, we place an hardware root of trust that can be an OpenTitan, a Calyptra, whatever it can be. And with that, we manage basically the access control to the system. And here, the RTL design is actually public, if you're interested. Also the verification part. Also here, as in Acre, what we did is that we are not the smartest here. So we want to do something that can be verified. So we provided a set of properties for the NOC to verify our access control system. And that can be also extended and can be used to verify our system. Finally, top, holistic performance analysis for critical system on chips. This is another work that we did with E.T.S, Zurich, Luca Benini's team. But this was more an analysis work. It was more an analysis work, timing analysis work. So as I mentioned before, there are not many work in analyzing hardware from the real-time perspective. We did the analysis of the system interactions for FPGAs that can be also used on ASIC, but we wanted to do something more. We wanted to do an analysis of a full system on chip that is open source. We need the code to do the analysis. And they have a lot of system on chips, right? And this is one of them is a cache, which is similar to Garfield, actually. It's a cache system on chip, which has CPU and a cluster, plus a memory controller and cache and everything. And what we did is modeling each of the IP. So looking into the RTL, we model each of the IP, understanding the worst case analysis, the worst case execution time for each of the crossbar, and the cache memory, and all of the peripherals, basically. And with that, we put together, again, an analysis, a mathematical-based analysis that you can use to upper bound the execution time of the interactions between a controller and peripherals. All right, I'm finished with previous work. Now it's time for new work. I'm going to be very fast on that. I'm almost done. So just like the current efforts that we have, just 2 slides, we're done. We're going. So what we're working on right now. So these are just the work I'm more involved with. And this is, first of all, SoC level hardware fuzzing. So I don't know who is familiar with, is anyone familiar with fuzzing? No? So software fuzzing is a methodology that is widely used in software for verification of C code, firmwares, and also higher level code. And it's basically a verification methodology in which you take a function or you take code and you just inject inputs that are not supposed to be like, you push the boundary of the inputs, basically, right? So, and the interesting part of fuzzing is that it's made to be adversarial. So it changes the inputs, and it has a genetic algorithm that evolves the input to make, basically in software, crashing the system. So in software is easy. So like you just crash, segmentation fault, okay, good, we got a good fuzzer. So in hardware, this is more complex because how do we know when hardware crash? Hardware execute anytime, you just give a clock, it executes forever, right? I mean, so it's more complex. There are a lot of emerging works in hardware fuzzing, mostly for CPUs, focusing on CPUs, for detecting side channels and strange ISA behaviors and stuff. There is not much on SoC level. So like on interconnect and communication, interactions. So we're working on that right now. There are some works, some preliminary works. But we found basically three lacks. So one is the missing of fair benchmarks, because everyone make a fuzzer and check against like a version of boom, and the other ones check like with another version, and they check with another CPU. And how do you classify like the effectiveness of a fuzzer if you don't have a benchmark, right? The second one is that the system level guidance, as I mentioned, like how do you know when the system crashes, how you guide it, and we're working on that, the second limitation. And the third one is like mutations. So how do you make mutations that make sense at the hardware level? Okay. And basically, yeah, what we're doing is a benchmark. We're already working on that. One collaborator of mine, Andres Meza, is working on information flow guided hardware fuzzing, information flow tracking. And also, we are working on a hardware mutation engine for SoC interconnect. So we're going to see where we're going to go with that. But yeah, it's an interesting topic to work on, timely. The second one, everyone is working on AI, right? So aren't we working on AI? Of course. So yeah, this is an effort I am experimenting with, actually. Agentic AI for hardware security verification. So Kastner Lab is very strong with hardware security verification. I am not the right person for that. I have collaborators that do on that, but I did something on that. But basically, like the motivation here is that security verification is very largely manual process. You have to write properties, you have to verify them. It's very, very tedious and manual process. the expert validation, in any case, remains critical. So you can't give an AI like something to verify and say like verify the security of this, right? So there are hallucinations, partial results, whatever. So we can't do that, right? So what I'm trying to do is to provide something that an agent that can ease the security verification part, but basically using the AI for orchestration, not for the validation. So basically, is a hybrid approach that in which AI use deterministic tools like simulation tools, verification tools, invoking simulation verification with properties, and it basically provides proofs of what you're asking. But it should provide like deterministic proofs of that. And our aim is to integrate that into continuous integration flows for regression testing. So whenever you do git push, you trigger this automatically, and you do regression testing. So to automatically generate, it can be fortnightly or something like this. So the goal here is to automate repetitive verification tasks, but keep the expert control for the decision. Concluding, we organized a workshop. This was the first edition. It was a DAC 2023, if I remember correctly, just because I have a nice flyer for that, so I put this. And we talk about open system-on-chip platforms and security and safety. So we invite people to talk. There is an open call for submission. I organized this with my friend and colleague, Brooks Young, and also with David Rossi and Luca Benini from University of Bologna and E.T.S Zurich. So we just got accepted for the third one at ICCAT 2026. So we're going to be there. Brooke is going to be the TPC chair most probably this year. And we're gonna have someone from NYU too in the organization most probably. It's not official yet, but stay tuned if you're interested in that. If you want to submit something or you wanna come in San Jose for ICCAT, we're gonna be there. Of course, all of this work, I mean, couldn't have been done without like all of the collaborators, all of the people that works with me and I work with. This is like some of the collaborators that for this specific work that I presented, okay? So, and then we collaborate, as Fernando mentioned, we collaborate with AMD, we collaborate with many other companies. But what I'm very proud of also is that we have collaborators from Universidad of Sevilla. So we've got Pablo here with us 3 months in California, and he did a fantastic job with the AI engines. They're very tedious to work with. They're very complex, and I mean, but it was a fantastic trip, and yeah, I hope that he had fun besides work, also like in California. Yeah. All right, wrapping up the takeaways here. If you want to bring something away from this talk, is that from my perspective, security and safety are system-level properties. So it's not just at the IP level, like checking the security of the CPU or the hardware accelerator or anything, but at the system level. Emerge things that are important and must be checked. What we're doing, the works that we're doing focus on bridging hardware design, safety analysis, and the security for new system on chips, basically. And we strongly believe in open source as a catalyst for innovation and trust. So we work with that, with open source mostly, and we are proud of that. So the marketing closing, automotive to healthcare, the future needs more robust SoCs. We're working on that. So thank you for your attention. This is my email. So if anyone is interested in that, please send me an email. We're very open to collaborations. And besides that, I want to thank Fernando, Pablo, Antonio, everyone here at University of Sevilla that invited me, organized to be here. It's always a pleasure to be in Spain. As Fernando mentioned, I studied in Valencia. I did my master thesis in Valencia. And I learned a little bit of Spanish, a basic Spanish for ordering a beer and surviving on the street, which is enough for me, yes. So thank you for your attention. If there are other questions.
Any more questions?
Thank you very much, Francesco. It's a pleasure to have you here, and it's a very nice talk. So Since here in the department we are working with not only as a research, but also for some company projects.
Sure.
With this talk, I keep thinking, so these FPGAs are not safe enough for commercial applications,
It depends what you care of.
like these security levels that
Sure.
some companies.
So the idea is that it depends on the threat model. The threat model. So who can attack? How much do I want to spend to avoid this to happen? Basically, right?
For example, for automotive,
For automotive, this is very relevant. For yes. For automotive, yes.
risk for
Yes. Then if there is like an FPGA board running inside of a small room that no one can access with people, with rifles and stuff like this, maybe it's like it's like less relevant, let's say. So it depends which application. It depends if it's connected. It depends who can access that. Like it depends a lot on the threat model, right? Who is your adversarial? This is the thing. Like you have a physical adversarial. You have a network adversarial. So like, it depends. That's the answer.
with this problem with the bandwidth
Sure.
balance. Is there a possibility for one of the accelerators or modules
Sure.
to be alone or to be isolated because of this risk? Or because of this
Definitely. It can happen. Sure. Yeah.
could be a problem.
It is, from my perspective, is a problem. So you're opening an open door. But I mean, when I talk with other people that are more performance oriented, they say like, it's like that's a performance thing, like so it's more. So yeah, I agree with you. I mean, it's a problem. We've wrote a lot of papers about that, right? So, but yeah, I mean, more broadly, it depends what you care about, right? If you want something cheap and dirty, like you have to make something works, and you focus first on making it works, and then making it safe and secure, right? So depending on how much money you have, what you care about, it's always a trade-off.
But the good news is that there are solutions.
There are, sure. Yeah, there are, definitely. I mean, all of them. Actually, I didn't say that I have my implementations. Some of them are online, some of them are not online. But the implementations of the technologies that they presented from E.T.S Zurich are all available online. So if you need them, you just go there and you have the RTL, and they're pretty good in writing code. So they're good and they're verified. So I mean, you can use them. Yeah. Sure, if you need them.
Very much.
Francesco, I wanted to ask you before, because I forgot to ask you before. I think it's like your fourth paper from the end.
Do you remember the name?
That is
Top?
That's. I wanted to ask you because as you say that you propose here a full modeling of the performance of the system and so on. I wanted to ask you because you have experience on that. For example,
Sure.
For our work on AI engines, one of the most problematic stuff is the network congestion when you just send data through streaming or with access to memory, for example. Did you model that stuff since you are working with the AXI?
Yes.
How do you do that?
So when you work with AI engines, you have a problem with the network on chip, and basically that you can't access the RTL code of the network on chip. Here we have access to the all RTL code. So we know exactly how the crossbars behave. We know exactly that when you send a transaction and the other send a transaction, which signal goes up, what is going to happen, how much is going to be the delay for contention, for traversing the interconnect, coming back and everything. So the magic sauce here is that we have the full RTL. If we don't have the RTL, you can just speculate, right? So you just say like, yeah, I mean, this is like, okay, this is a router, it's taking like X clock cycles to cross and everything. But here we have everything. So yeah.
Okay.
But yeah, read the paper. It's very heavy. I mean, there are a lot of formulas, but yeah, they're very heavy papers. This one, they're very heavy. Yeah, but yeah.
Okay. I see.
more questions? Well, Francesco, it has been a very good conference, with seminar. We have learned a lot about the background concept, and then I want to ask you a general question.
Sure.
About the Moore's law. What do you think about the axis evolution with related to the bandwidth that current AI application are doing? Do you think that axis is going to increase the bandwidth to support
So yeah,
AI application?
it's a good question. So AXI basically it's something that can be used just when you have space to deploy 65 signals, right? So it's something just at the interface, right? So AXI is pretty flexible. So if you want to go higher bandwidth, you can go up to, I think the bus width of AXI can be up to 1024, and for the moment is enough. But the most interesting, like the most important part is that like after AXI, you go down to NOC and become everything serial, and you go faster with a small single link. And over there, the problem is always the scaling problem of the interconnect, right? So whenever like you scale with interconnect, there is a problem. And yeah, right now still the memory bandwidth is still one of the major bottleneck with AI applications and in general, like data-hungry application.
What are the main physical problems to increase the number of
space? I mean, area, right? So I mean, generally speaking, when you go off, like you make an AXI interface, and then you go like in a network on chip, for instance, right, which are the one that provides like highest performance eventually. When you go off, you go just with a single link, or you go with like 2 links, because in that case, like you can't fit like that many signals, right, and be fast. So it's like it's a trade-off of space. Yeah, definitely. Yeah.
A specific question.
Sure.
I understood that you are trying to classify the different channels for the communication of the axis bus. But is there any individual specific proprietary channel to manage the threats, to detect threats, to manage internal protocol, and this channel cannot be used by the rest of communication? Is there any?
There is not. I mean,
independent channel to.
Like you mean dependencies among channel, or you mean like there are channels that cannot be used by an hardware accelerator or something like this?
Cannot be used by any
that cannot be used.
It's a proprietary channel to manage the control, the threat, etc. So.
No, you can do like, you're talking about like a security bus or something like this to manage the control or something like this. Yeah, you're talking about that.
Device or inside the axis bus.
There are
specific part of the bus that cannot be used by the application.
So according to the specification of the standard, you can basically implement as you want. Then according to the implementation, if you want, you can reserve something, right? Then it depends when you put things together that are heterogeneous. All of them should reserve that. So it should be like everyone should behave in the same way. And the problem is that when you are heterogeneous, maybe, yeah. But yes, makes sense, sure.
So again, I come to
thank you, Fernando. Thank you so much.
You want to share your.
I can share my slides. Yeah, sure. Yeah, so I can share my slides.
I don't know when the conference will be open to the public. If you want to take a look over this conference.
Sure.
But I would to ask Jose Maria about the recording of the conference.
Sure.
So bye-bye. Thank you for your attention.
Thank you.
See you.